All right, folks, let's do number 5. All right, let's get started. So I'm going to draw the graph here. This won't be to scale, but whatever. I suck. So this is going to be the x-axis, and this is going to be the y-axis. So a fish is swimming. So let's just pretend you're looking at from an up-down view or whatever the heck. In a horizontal plane that has a velocity, and that's at that, and that's a vector. So that means I'm going to rewrite this as the initial velocity of the fish is going to be 4 meters per second in the I hat direction, minus or plus, in this case, 1 meter per second in the j hat direction. And the position of the fish, even though we're going to, this is why I like to write them in my own notation, but that's fine. I'll make an exception here. We're just going to pretend these are points in there. 10 meters in the I hat direction. I'm going to call that R naught. I don't care what the heck you call that, but plus, except for I'm not going to use that I initial symbol. I'm going to use this symbol instead, so forgive me for switching around a bit. But you guys can switch back. I mean, you're not that retarded, so who cares? So anyways, so this is going to be R naught is going to be for 10 meters in the I hat direction, plus minus 4 meters in the j hat direction. What is that? That's 10 here and 4 here. That's a point. Beautiful. So that's going to be R naught. That's going to be that specific point where it's going to have a velocity. I'm going to put in blue here. That's going to that's going to have something like that. That's going to be the initial velocity. In fact, I like to put green here. So the initial velocity is going to be this. I like to use. There we go, folks. That's very beautiful. The Earth is flat. It's proven scientifically. Anyways, let's move on. So this velocity and the x-axis and the y-axis is, this is the position. That's the velocity. All right, folks. That was just the setup for this first part. All right, let's keep reading. After the fish swims with the constant. Oh, and also let's emphasize that this is the point at 0 seconds. So at 0 seconds, that's where the fish is, and that's the component of the velocity is. And it's going to accelerate, so that means it's going to change the component of its velocity. And it's going to accelerate for 20 seconds. So at t equals 20 seconds, I'm going to write that down somewhere. I don't know where the heck to write that, but t equals 20 seconds, its final velocity is this. So after 20 seconds, its final velocity is going to be 20 meters per second in the I hat direction, minus 5 meters per second in the j hat direction. Beautiful, folks. So that's the final velocity in the 20 seconds. Now the question is asking for part A, what are the components of the acceleration? Well, in order to get that, the acceleration vector, and they want the components, is really just going to take the final velocity minus the initial velocity divided by the course of 20 seconds. You could say T1 and T naught or whatever the heck. So I'm going to say T1 minus T naught just to make it complete. Beautiful. All right, let's do the math. So the acceleration is going to be -5 minus 1. So that's going to be -6 meters per second in the j hat direction. 20 meters plus that, that's 16 meters per second in the I hat direction. That is the change of the velocity over the course of 20 seconds. So therefore, once you do the math calculation or whatever the heck, you would have 0.8 meters per second in the I hat direction, minus 0.3 meters per second square in the j hat direction. I was about to screw that up, but glad I didn't. So there we go, folks. That is part A, what they want. All right. Beautiful, guys. Look at that. All right, guys, let's do part B. What is the direction of the acceleration to respect to the unit I vector? Well, the direction is really just tan inverse of arc tan of 0.3 divided by 0.8, that's going to be down that negative, so you can take 180 degrees plus that thing, or the, I don't know, 360 degrees plus minus, put a minus sign, do whatever the heck you guys want, I don't care. Anyways, the angle is going to be, so once you do the math, so this angle is going to be 360 degrees plus arctang, however you guys want to find your angle, it doesn't really matter, divided by 0.8 is going to be 339.4 degrees. Beautiful, folks. All right, now part C. Sweet. Now this part, this part is a bit involved. I'm surprised this is blue and this is not red or something. Where is it at t equals 25 directions, and what direction is moving? But before we do this problem, understand that it's emphasized that it has a constant acceleration for 20 seconds. Now, what's very strange about this particular problem is that it could just be asking what is its position at 20 seconds. Since we're finding all these components, it's just kind of weird that they're asking, like, all of a sudden, what is position? Whatever, I don't care. So anyways, if the fish, okay, so let's come up with the position vector, call it the parametric equation, into respect to the variable x and y, which has embedded in the x variable t. So in order to do that, beautiful, let's write this parametric equation so we can get this out of the way. And I'm going to put parentheses to emphasize that this is going to be the x. So the initial position is going to be r naught, which is going to be 10 meters. I'm just going to write the whole thing. I was going to write in terms of vector r naught plus v naught t plus a component t squared over 2. In fact, that's what it is, folks. Before I do that, let's write that. So this is what I'm going to be doing. I'm going to be writing nothing more than r naught vector plus v naught t plus a t squared over 2. So since we already found the acceleration vector, this is already going to be the whole position depending on the time variable. That's the parametric equation right there. So in other words, this is going to be 10 meters plus the initial velocity in the x component, which is 4 meters per second. And since we're finding it at a specific time, I'm just going to put t in there just to set it up for you guys. Or in this case, let's just put 25 seconds already. All right, so this is going to be 25 seconds. I'm just going to put the whole thing in there because I'm way too lazy right now and I'm getting really tired of these problems. Plus 0.8, or 0.4 in this case, 0.4, 25 seconds square. So this would be meters per second square. So that's going to be square the whole thing. So once you find that, so that's going to be in the I hat direction. And we're going to put the I'm going to put the j hat underneath here. Plus, what's its initial position? Negative 4 meters. Plus 1 meter per second square. Times 25 seconds. Minus, this is why I have to slow down because I'm already losing track. I'm too high on the edibles at the moment. So 0.3 meters per second square divided by 2 times 25 seconds square. Yay, I did it. All right, guys. So that's going to be in the j hat direction. All right, so once you put that in the calculator. All right, so once you put that, the answer for part 3 is 360 meters in the I hat direction minus 72.75 meters in the j hat direction. So folks, that is how you solve these problems. These vectors, they're a bit involved on this one. So there you go, folks. That is the answer to part A, part B, and part C. I hope this helps you guys. All right, bye.